Hello class, this is Adam Ward. I wanted to work through an example with you looking at pathogen transport. The scenario that we're going to consider here is a point source of bacteria entering an estuary. We're given information about the physical characteristics of the estuary, light intensity, light extinction coefficient, and fraction of seawater. Notably, there's no settling of bacteria in this problem, and we're asked to find the die-off rate or the removal rate for bacteria, and then to find what steady state mass loading we could put into this estuary if we want to keep ourselves below 1,000 per milliliter. Perhaps that represents something like a full body contact recreation level that would be safe. And notably here I had given you that coefficient as D, but most properly with our semester that would be a capital E, representing both diffusion and dispersion. So first problem, as we went through in lecture as well as the textbook, we can consider mortality, death due to light exposure, and settling as the three removal mechanisms. And if we go ahead and plug in values here, we've got 50% seawater, 27.5 degrees Celsius in the first term. In the second term, we're assuming that the value of alpha is 1. Light intensity of 200 Langleys per day. 1 Langley is the same as 1 calorie per centimeter squared. And you'll note that I'm converting that into hours. Double check the equations in the textbook. You'll see that that's the proper units. We need to put that into the equation. Extinction coefficient and depth on the bottom, and then completed the same in the exponential. And the final term is plus 0 because there is no settling in this problem. And so I calculate a die-off rate or a removal rate of 8.7 per day. Now, with that information, we can address part B, which is the steady state loading that's acceptable to keep this value below 1,000 per milliliter. And this is an estuary with a point source. And so if you look back to, I believe, lecture 9 in your textbook, you've got an equation that looks like this to describe what happens in an estuary. We can make two simplifications here. The first is that we can recognize that the worst case location would actually be at the point of discharge, as moving or advecting in the estuary as well as spreading would reduce those concentrations as you move away. So at x equals 0 would be our worst case scenario, and the entire right hand term as shown in red becomes equal to 1 then. Also remembering the definition for the estuary number, we can simplify and reorganize that equation as shown here. And if we go ahead and plug in values for discharge, for concentration we'll use our acceptable value of 1,000 per mil, and we're going to convert that into meters cubed to keep our equation dimensionally homogeneous. And then in the square root there, 1 plus 4 times that die-off rate we calculated, 8.7 per day, times the dispersion coefficient of 10 to the 6th meters squared per day. And on the bottom we've got velocity squared, and you can see in red I've gone ahead and calculated that based on the given discharge and cross-sectional area information. And so I come up with a final value of about 2.36 times 10 to the 15 per day that could be loaded into this estuary to maintain our goal. Notable assumptions that are embedded in here. This assumes that the bacteria are added with negligible Q in. So sort of a lateral inflow that's a bacterial load but not a significant discharge. If there were, that would increase dilution and possibly also increase flushing through that estuary, and the problem would be more complicated. And as a reminder here, we're also assuming that there was no background concentration, and so if we had some background level due to natural ecosystem processes, then we would want to subtract that off and have used something smaller than 1,000 as our target concentration. I hope this helps you see how to work with pathogens and demonstrates how all of the equations we derived early in the semester can be applied to any of the constituents that we're currently working with. Thank you.